Hey, good. So I have uploaded the graded midterm exam on Avenue to Learn. You will be able to see your score on there. So basically, for most of you, most of the class, you are doing well, except for the first question, the probability theory. This is the question is trying to understand how much you know about the probability theory. It's rarely touched in the class, but it's very important for a lot of topics in this class. Most of you are doing well for the first part of the problem 1, but not for the second part. I have uploaded the solution on Avenue to Learn, and I will see whether I have time today. If we have some spare time today, I will go through the solutions on about the midterm exam. And if it's not, you can always go back to check the solutions and also the your graded exam. And feel free to let me know if you have any questions or any concerns about the grade. And well, you can always contact me for any questions. So that's the exam. Does anyone have any questions about it? Okay. If no, then I will try to start the lecture today, and actually we will have 4 lectures left for this term. I plan to go through the spend 2 lectures for the discrete choice model first. If it's different from our previous plan, where I want to introduce the tutorials for the Queen's OD and Transcat, but I want to put them to the last 2 sessions. With that, you will get all the necessary fundamental knowledges for you to work on the final project. By the way, for the final project, I will upload the final project on Avenue to Learn this maybe by the end of this week, and also upload the last homework assignment. So with that, you will have all the tasks you need to work for this class. So to work on the final project, you definitely need to know what is a discrete choice model, how you're gonna use the to calibrate the model to conduct the route choice and mode choice step in the for the transporting planning. So that's the plan for the rest of this term. Do you have any questions, any concerns about it before I start the lecture?
Doctor, I was just wondering if we could know the average of the midterm, just to know where we stand.
Yeah, the average of the midterm would be around I haven't calculated, but it would be around the 75 to 78, around that value.
Okay.
Yeah.
Okay, dear. Thank you.
Yeah. Okay. Okay. I have no questions. I'm gonna start lecture today. Go to the presentation mode, and I'm also gonna check whether it's recording. Okay, it's recording. Good. Okay. So for the just a moment, let me do this one again. So it looks like there's some issue about this. Just a moment. I don't know what happens, but I always like the presentation mode cannot be compiled with the yeah. Okay, let me share it again. Okay, it's working. So in this chapter, we're gonna go to the introduction about some fundamental knowledges of the discrete choice model. And in the next lecture, we will continue this topic, but we will focus on how this model is applied for the mode choice and route choice, and how it's gonna be extended for more complicated problem. So for the discrete choice model, this is especially designed to solve the third step of the transform planning, where you will be asked to make a decision about which mode you have to take or which route you need to take. For example, if you decide to travel from Hamilton to Toronto area, you will have multiple choices. You can drive your own car, you can take the bus, or you can take the train. For each mode, you need to spend different amount of the money. For the car, it will be faster, but you need to pay for the gas, pay for the parking. For the bus, it will be the cheapest one, but it will be very slow. And also you need to consider the time you need to walk to the bus station and the potential waiting time at the bus station. And for the train, it's faster, but the ticket is relatively more expensive, and also need to plan your trip ahead in order to catch the schedule of the train. So for each route, for each mode, you have different costs, and of course you have different benefit to use each mode. Like if you drive in the car, you have good privacy, you have flexibility. If you take the train, you will be more comfortable. So you have to, if you plan this trip, you have to make a decision which one you want to take, and your decision is based on the consideration about this cost and this benefit. Or we can probably consider that this kind of utility that you're gonna use. And then in this step, in the third step about mode choice, we want to find out in the mathematical model to describe how the each user is making a decision, and that one relies on the discrete choice theory, which will provide give us some fundamental theories about how to make the selections from the individuals. Here, let's start with the theory part. First, let's consider the set of the alternatives available for individuals. For example, the different type of the transforming mode. We assume that there is a class of the alternatives. Say that j different alternatives from that will be Cn to represent the j different alternatives, and isn't a group a sample space that we can take. Now for each mode we define a utility which is called the UKN to represent the individual user n to use the alternative or the mode k from the sample. And now for each mode we know the utility, and we need to use this utility to make your decision. Basically to make the decision for each individual, you want to maximize your own utility. So if you have j different alternatives, the one that you're going to choose is the one with the highest utility. For example, if the mode I has the highest utility, then you're going to choose it. And so that's the simplest rule for the human drivers to, or not drivers, for the people who are trying to plan their trip. So that's the key assumption for the discrete choice theory. For each individual, they will always try to find out the make a decision based on maximizing the utility. And now, based on the definition, we need to think about how we're going to estimate the utility. Find out the most accurate estimation of the utility is the key component, is the key step for you to decide your decision. In the discrete choice theory, we assume that the utility will be in the function of the set of attributes. Assume that we have p different attributes, and that will be for each mode we have the x1k, x2k, until to xpk different utilities. And if we want to know more, make it more specific for each individual, you can specify them as xkn, where n is the utility, the attribute for each individual, as the even for the same attribute, same variable, it might be different for different users. So we have the x1kn, x2kn, until you get xpkn for the individual n with the mode k. And regarding to those attributes, it could be the travel time. Say that the first one could be considered as travel time, and it could also be the fare price of the tickets, and so on. Let's just take the travel time as the example for one attribute. For the mode K, you have a travel time. Say that the travel time is about 5 minutes for the individual n. Then you will have the value for the x vector for the individual n. And similarly, you can observe the attributes for the other attributes for the specific mode and the specific individual. And those would be the independent variables for you to estimate the utility. And usually, to consider the estimation utility, we can use the simplest function, which would be the linear function, assuming that the utility is the linear function of the attributes. So here in this function, theta is the coefficients we have to estimate or calibrate from the observations. And this is also defined as the utility weights, which is usually applied for the estimation of the utilities. So that's the vector we're gonna calibrate from the observations, and with that you can write the utility as the function of the attributes and the coefficients in the matrix format. And of course, you can extend this one for all different individuals and different mode. And regarding to the decision, this one is a little bit tricky. It's different from the conventional linear regression problem. For the discrete choice theory, our output is the decision of the individuals. But for each individual, they can only choose one mode. They cannot take a bus and the bus and the car at the same time. Well, unless we are considering the multimodal transportation, that would be a different story. But usually for the discrete choice theory, based on the definition of the decisions, each user will only choose one mode or one alternative. So for the output vector with respect to n individuals, for the individual n with j different alternatives, they can only choose one. If the alternative I is chosen, then yin is 1. If it's not chosen, then it's always 0. So for each individual, there's only one cell with the value of 1. The others will be 0. So that's the decisions for the from the each individual. And now we need to use this output y and the observed attributes to develop the discrete choice model for us to identify how we're gonna model the decisions of the individual. Now the difficult part is like for the utility. If we go back to check the utility, this is some value that we cannot observe. Utility is just some value we defined to make a comparison about different alternatives or different choices. It does not have any physical meanings. What we have is the decision. It's the either 0 or 1 for each mode. And we have to use this information to make a decision to calibrate the model. And so to sum it up, for each individual with j different alternatives, we can define the utility for each one of them with the linear equation with respect to the a set of the attributes. And for each mode, each individual will have one decision. It's either 0 or 1, but some of them there will be only one with the value of 1. And regarding to the choice problem, for each individual, we want to choose the one which can help you to maximize the utility. So the one you're going to choose will always have the highest utility based on the function you defined, the linear function you defined. And it's subject to the constraint, so that each individual can only choose one alternative or one transporting mode. And that one give you all the optimization problem for the discrete choice theory. So we have the output as y, and we have in this to write down this one to the matrix format. We define the vector b. Vector b represent the utility of all the mode, and the utility is a linear function of the attributes. So that's the optimization problem for the discrete choice theory. And now let's dive into more details about how we can expand this matrix format.
Sorry, doctor.
Yes.
Just a small question. I just want to make sure that the thing that we want to calibrate is the coefficients, right?
Is the coefficient. We want to find out what's the value of theta. Yeah.
Oh, okay. Okay, perfect. Thank you.
You will be provided with the value of x. So x is the attribute you're going to observe, and also capital Y, that will be the observed decision for each individual. So
thank you.
Yeah. So I'm going to give you the details about how to do the calibration and give you the examples about the way to do the calibration. Okay. So now let's go to see the expansion. And if we go to check this equation about the one that we defined here for Bn, which is theta times x1, theta times x2, and so on. And times y will be the decisions of the individual with respect to different mode. That will be the y1n, y2n, and yjn, and so on. You can write them into 1, into, so this one can be written into this linear equation, and that's the utility for each individual with respect to all the alternatives. And also, I'm trying to erase this one. And also for the constraint, we can only choose one mode. So if we summarize or do the sum for all the decisions, the value should always be 1. So that's what we just claimed. And with that, you will see the decisions. Only one going to be selected, and the rest will be 0. And then we can make some statement about the try to make some statement about the discrete choice theory. First, we're gonna have the linear function for the utility function will be linear, and it will be the well, we choose this one, choose the linear function because it's the best first order approximation about the relationship between the attribute and utility, and also the simplest one. And so that's the reason for us to choose the linear model. And also the specification of the attributes will exclude some aspects, the minor, definitely those minor aspects. We only choose the one which will be very important, have a significant impact to the model. For example, still go back to the example for you to take the trip from Hamilton to Toronto. The travel time definitely is a very important factor. The fare price is also important, but probably regarding to the some other factors, like if it's in the summer, the weather conditions like the sunny day or the cloudy day may be a minor factor, and they can exclude them to the from the model. So this is just one example. Still depending on the decision, how you're gonna make the depending on the users and how the entire system looks like. So with that, we will only choose the one. We only choose the important factor to do the model, and so xk will be carefully selected. Only choose the some of them. Only choose some of them from the a group of the attributes you conduct from the survey. So that's say that from the survey you get a p plus q attributes, but you only choose p of them. So that's the first thing. And second, there are for the discrete choice theory, we will also need to introduce some randomness for the model, because the usually the behaviors of the human beings cannot be modeled perfectly by the statistical models. There exists some randomness there. So we will consider that the utility is also a random variable, and the decision making is also a random variable. For example, for some day, for the example, for you to travel from Hamilton to Toronto, well, if for the 10 trips, you probably choose 9 of them as the using the car, but maybe one day you're going to choose the bus. So it depends. It's not an deterministic model. Instead, it's in a random. It's in a random model, and we want to introduce the impact of these random terms. So all those kind of disturbance to the model. So with that, the model can be revised by introducing a random term. We say that is epsilon y for each individual, and it could be applied for any particular candidate solutions. So that's what we do for the to extend the discrete choice theory, and we call this model as the non-deterministic optimization problem. We need to because they have some probability there, and we still want to find out the maximization of the utility. This is the kind of the combination of the probability and optimization problem, and it will bring some difficulty. Similar to the linear regression problem, but it's more difficult to consider that the output is just some binary variables 0, 1. So let's see more details about how we're gonna solve this one.
Excuse me, Professor.
Yes.
I had one. Can you please go back to the previous slide?
Yeah.
So in this, you say that we'll exclude some aspects. So basically, only continuous variables can be included in this linear model.
Not really. It could be some category variables. It could be considered as the binary variables. I believe you're talking about those. The variables could be applied for capital X, right?
Yes.
Yeah. So it could be the continuous. It could be discrete.
Okay.
Both of them are possible. Actually, you need to consider the discrete variables, attributes for the model. That usually you need to add one constant term for the discrete choice model, and that term is involved with the mode, and with that is a discrete variable. I'm gonna for the maybe at the end of this lecture, there's one example to show that about how to set up the attributes, and you're gonna have the idea about how we can include both discrete and continuous variables.
Okay, thank you, Professor.
Okay, and now we have this kind of maximization problem. We will have the deterministic component and also the random term. We can also just try to write them into revised, define new matrix B prime, and put the random term inside. So that will be B hat. Sorry, you define a new variable B hat. The B hat will be the deterministic component plus the random term, and these two will actually be equivalent to each other. We will just try to merge the random term to the matrix operation so that we can get some simplified expression for the maximization problem. And here you will see that for the linear regression part, theta times x would be the one can estimate it from the model, and it's the deterministic component. So we define a new variable v1n to represent the deterministic utility, and epsilon will be the random term. We define it as the random utility. So combine them together, that will be the actual utility we're going to use. So that's the model, the revised model, and as I just explained, we will have the deterministic component. It's just a part of the utility, and we have the random component, and it should be applied for us to calculate the probability for you to take each mode. And now the solution, say that if we are trying to if we choose the for the individual, if you choose the mode I for your trip, then it must means that the utility of I actually higher than the all the other utilities. So that's the case. So the utility of I is higher than all the other alternatives, and the UI is the maximum value of all the U values. And if we write down them to this to write the expression, the linear equation we defined, so that would be the theta times x plus the random term is higher than the expression for the other alternatives. That is exactly as what we just mentioned. UI is higher than UJ. And you know that here for the for this probability issue, if we want to find out what's the probability of this one, we need to define a probability density function for the random term. This is usually arbitrarily assigned. So once the distribution is defined, we will then be able to provide or do some derivation to get the expression about the probability as the function of the coefficient and the observed attributes. And this is what we're going to do for the following slides. So let's before we go to the actual distributions that we're going to use for the discrete choice model, let's see in a simple example. Here let's consider the behavior of the group of the travelers with respect to two transporting options, A and B. Consider A is the car, B is the bus. And the travel time for these two modes would be TA and TB. And we also have the formula, the expression for the utility for these two modes. For the mode A, UA equal to alpha times TA plus beta times I, and I here is the income level. And for the utility of B is not related to the income. So UB actually equal to alpha times TB. So that's the utility definition of the utilities for the two different modes. And now we want to find out what's the probability for the individual to take the mode A or take mode B based on the given travel time at mode A and mode B. In addition, in the problem, we have an assumption about the distributions of the income level. Assuming that the income level is in a uniform distribution, and the distribution varies from the income is uniformly distributed from 5,000 to 25,000. So that's the constant value, which would be if you write them to the equations, you get the value as 0.5 times 10 to the power of -4 if I is between 5,000 and 25,000. Otherwise, it's 0. So that's the distribution for the income level. And also for this problem, we assume that alpha equal to 0.05, beta equal to 2.0 times 10 to the power -4. And with this problem, with these assumptions, we want to find out the probability that the traveler gonna choose the option A as the when you are provided with the value of TA and TB. So that's the all the assumptions we made. Now let's see how we can get the solution. So basically, for this problem, if we want to find out the probability of choosing option A, it just indicates the probability of UA higher than UB. So this is what we actually want to find in this problem. And alpha and beta would be the constant. TA and TB would be the input variable. It's not a random variable, but I is a random variable in this problem. It follows in a uniform distribution, and that's the part we have to deal with. So to do that, we will first go to check the uniform distribution. For the problems of choosing the mode A, that is probability of UA higher than UB. And we know the expression of UA. UA is alpha TA plus beta I, and UB is alpha TB. And in that sense, we can try to write down the expression of the probability to choose the mode A. That is alpha TA plus beta I higher than alpha TB. And you do a little bit transformation about this expression. You can get the value as the probability as I is higher than alpha times TB minus TA divided by beta, which is 1 minus the probability of I smaller than that value. This part for the second part is actually the this is the probability, the cumulative density function, the CDF of the income level. So we can further simplify this one as 1 minus capital F alpha times TB minus TA divided by beta. This capital F is just the CDF of this distribution. And so that's what we want to calculate. We need to find out what's the expression. What's the expression of capital F? As F follows a uniform distribution, the the estimation of the capital F would be relatively simple. For the uniform distribution, you can actually see that actually for this case, for this specific distribution, if alpha is less than not alpha, if the term A represents the alpha times TB minus TA divided by beta, if A is less than 5,000, which would be the part on the left side, definitely FA will be 0. But if A is higher than 25,000, then it should be 1. For those in between, as this is in a uniform distribution, so you're going to have the line to connect these 2 points. So with that, we have the we can derive the distribution, derive the line from between 5,000 and 25,000. So that one give you the probability between 5,000 and 25,000 with this equation. So solving this integration problem, you get the result as you can simply get the result as FA is 0.5 times 10 to the power minus 4 times A minus 5,000. So this is the CDF, of the not the income, the CDF of the A, and it's actually represent the income level, but we're gonna need to convert this one to the variables of TA and TB. So what do we do for the next step is how to convert or change this the value of A back to TA and TB. It should be in a function of TA and TB. So first for this for the original formula we derived, the probability of choosing A is 1 minus F times alpha times TB minus TA divided by beta, and A is this is A as we defined, and we have already derived the CDF. And now if we put all the values of A, the alpha and beta in this equation, you can get that A actually equal to 2,500 times TA minus TB. And for the CDF, for the first case, if A is less than 5,000, you can get the condition when TA minus TB is less than 2, the FA is always 0. And similarly for this part, you get the value as when TA minus TB is higher than 10, then the CDF is always 1. And for those in between, you can still derive the formula. So what do we get for those in between? For those in between, if we replace A with 2,500 times TA minus TB, you eventually get that the probability of choosing A is 1.25 minus 0.125 times TA minus TB. This only applies when TA minus TB is between 2 and 10. And for those below than 2, that is 1. For those higher than 2, higher than 10 is 0. So this is what we obtained for the how we're going to choose the mode or the alternatives based on the utility function and under the specific distribution. Of course, this is a simple example. What we should do for the discrete choice model, we want to expand this one for some general case. So let's go back to what we have defined previously. First of all, consider that there's a set of the alternatives which will be available for the individual n. So as what we defined previously, we have J different alternatives, and we also define the utility for each individual with respect to each alternative. And we have the deterministic component and the random components for us to estimate the utility. And usually for the deterministic component, it's defined as a linear function, and we can write them into the deterministic. Apply a new variable v to represent the linear component or the deterministic component. And for the individual to choose the mode I, that indicates that the utility I is the largest one compared with the other mode. And that will be the probability of the UI higher than UJ. And this is the probability we want to find. And we also have the expressions with the deterministic and random components. And here you can see that in this equation we have two random variables, epsilon I and epsilon j, and we have to think about how the distribution of these two random variables will affect our estimation about the probability of choosing the alternative I. And you can do some slightly revisions about the formula inside. So we get the probability of the epsilon j smaller than vi minus vj plus epsilon I. But here you have you see two random variables. So with that calculation of this distribution, you must have to consider the joint probability of multiple variables. That will also increase the difficulty of the derivation. But for this problem, we have to consider all of them, all the random terms. And of course, we know that the deterministic component is determined by the observed attributes and the coefficients that we have to calibrate. So in this case, those parameters theta, they are null and they need to be calibrated. And we can also assume that usually these parameters are independent to the individuals, which means that for all the individuals in the model, they share the same coefficient, and we're going to use this one to this one is actually similar to the linear regression problem, but we will extend this idea to the discrete choice model. And regarding to the attributes, they are all null, could be observed, and it's the key component for us to conduct the calibration. And so that will be the overall model. And now let's see how we can find out the probability of choosing the alternative I. Assuming that you are provided with the PDF, the probability density function of the random terms, and also you can get the CDF, the cumulative distribution functions for the same variable. And then in this distribution, we can first discretize the continuous probability density function into some small piece, some small intervals, and the center of each cell. We know the center of each cell is at T1, T2, T3, T4, and go to Tk and T infinite and so on. And we define the boundaries of the two. We can define the boundaries of the two ends by assuming the width of the interval is delta Tk, and then the left end is Tk minus delta Tk divided by 2, and the right end is Tk plus delta Tk divided by 2. So that's how we define the discretize the random the continuous variable continuous distribution function to the discrete ones to simplify to help you understand how the equations in the previous slides is derived. And also we will be able to find out the total probability in each cell. In this case, for the interval of tk, the total probability would be the probability of tk. Probability of t is between tk minus delta tk divided by 2 to tk plus delta tk divided by 2. And here the as we discretize the distribution into small cells, and we assume that the value of the probability, the PDF, is constant in that cell. So this one can be further simplified as FTK times the delta TK. So it's just the area of this yellow region. And now regarding to the CDF, based on the definition of the CDF, for any specific value, say that A, the red region on the left side of the A, the yellow region on the left side of the A represent the probability when the all the values are smaller than A. So that's the definition of the CDF. Now we're going to use these two fundamental definitions from the probability theory to find out what's the probability of the what's the probability of choosing the mode or the alternative I from J different these options. So first of all, let's assume that this the first one is the probability density function for the epsilon I, and then we can find out the probability of the yellow region. That is the epsilon I between these two ends. And for the one below, we assume that is the probability density distribution, the cumulative distribution function of the alternative for the random term in the alternative J. And the yellow region represents the that the J is less than Vi minus Vj plus epsilon I. And here we just assume that A equal to Vi minus Vj plus epsilon I. So now we have these two probabilities, and we want to use these two definitions from the graph to find out what's the probability of choosing the alternative I. So as I mentioned previously, to do this calculation, we have to consider the joint probability for the two variables. So you can quickly expand this equation, and for that one, you're gonna start with the each cell from the first cell to all the other cells to the end, infinite number of the cells. If the value of TK falls in the first cell, then you can calculate the probability of that region times the probability that the epsilon J is less than Vi minus Vj plus T1. So that's for the first cell. And then you can also do the one for the second cell and third cell and so on. So that's the probability of I with all different possible values of the epsilon I. And if you summarize them together, you can get so that's here give you more details about how they are calculated. If you summarize them together, based on the randomness, the independent features of all the random terms, for all the J in this selection in this alternative sample, you can get the full expression for the probability of I to J by replacing the the capital J minus 1 different alternatives in this formula. So that is so for this part, you can see how it's going to be expanded. So I'm gonna try to skip the process about that one. It's quite complicated. It's just some fundamental definitions of the probability. You can go to see the how they're gonna be expanded, except the component about I is missing because the J should not be equal to I. And to simplify this one, you can apply the product sign for the probability of the epsilon j is less than that value, less than vi minus vj plus tk for each cell. And that's the expression that we're going to do for the probability of choosing the mode I. And if the value of the delta tk is small enough, if the value is small enough, then we can write them into the integration format. For the another thing I forgot to mention is like for the one on the left side is just the probability of each cell with respect for the one that we defined. For the one on the right is the cumulative distribution for the value less than this value that we calculated, and put them together, you can get the full expression of the probability. But if the delta tk is if the width of the cell is small enough, we're going to have the integration of the whole expression. So that would be the integrate of f epsilon I t. This is the probability distribution function for the epsilon I, and the capital F epsilon j. This one shows the cumulative distribution for the epsilon j, and you can do a simple conversion to move the dt to the right end of this expression. And those would be in this equation. You can see that we need to know the formulas of f, the probability distribution function, and capital F. That would be the cumulative distribution function in order for us to find out the expression of the probability. And this is a little bit tricky, and we have to make some assumptions for them. First of all, we need to assume that the epsilon j for all the alternatives, they are independent to each other. Also, we assume that they follow the same distribution. This is the same to what we defined for the linear regression. In the linear regression, we assume that the random term are independent to each other, and also they follow the same distribution, which we assume that is the normal distribution with the mean of 0. Similar things will be applied here. We assume that the epsilon I, epsilon j are independent to each other. They are identical, follow the same distribution. In this case, we will not assume that they follow the normal distribution. Instead, we assume that they're gonna follow the Gumbel distribution. There are a lot of advantages for us to introduce the Gumbel distribution for the discrete choice model. With this kind of identical features, so the function of probability distribution function and the cumulative distribution function will be independent of the individuals and independent of the mode. So that's the assumption, and we can then, based on this assumption, we can then further simplify the expression for the probability of choosing the mode I. And then we need to see what kind of distribution we can apply. Actually, for this one, for this expression, it can be applied for any distributions, normal distributions, gamma distributions, beta distributions, gamma distributions, and so on. But there will be a lot of studies about investigating the potential distribution can be applied for the discrete choice model. And the best one is the Gumbel distribution. So what we do is that here we assume that the random term follows the Gumbel distribution, and all these random terms are independent and they are also identical to each other. These two formulas shows the expression of the Gumbel distribution. The CDF is actually much simpler compared with PDF. So there will be a lot of unique features for us to for the Gumbel distribution, which can help us to simplify the analysis of the discrete choice model. Even though for the distribution itself, it looks complicated, but those features can simplify those analyses and give us a very simple expression for the discrete choice model. So for the Gumbel distribution, it actually has two parameters. The first one are the mu and eta. For the mu represent the well, it actually applied to represent the mean value. Eta is another factor to determine the shape of the Gumbel distribution. So usually we write the Gumbel distribution as Gumbel, eta, and mu, or we can try to just simplify this one as the epsilon, eta, and mu. So that's the assumption we made for the Gumbel distribution. And here I will give you the figure to show how the Gumbel distribution looks like. This is one standard Gumbel distribution with the eta equal to 0 and mu equal to 1. You can see how the distribution looks like. It's like on the left side, it's well, when the value of t is negative, it's a little bit concentrated to the y-axis. But on the right side, it's the slope is a little bit flatter compared with the trend on the left. It has some similarity to the normal distribution, but of course, you can clearly see the difference between these two different between the Gumbel and the normal distribution. And also, you can find out the probability then the cumulative distribution function for the Gumbel distribution. You can see how the probability is increasing over the time. So that's the two graphs to show the Gumbel distribution. And now let's see some good features that we can use with the Gumbel distribution to improve for us to derive the discrete choice model. So these two will be the PDF and the CDF of the Gumbel distribution. For the mean, the mode is the for the Gumbel distribution with the parameter of the eta and the mu, the mode is eta. So this is where the highest probability can be observed. For the mean value, that equals to eta plus gamma divided by mu. Here, gamma is the Euler constant, that is 0.577. So the mean is only determined by the two factors, eta and mu. And also we can find out the variance. The variance is pi squared divided by 6 times mu squared. For the there's another quite useful features of the Gumbel distribution. First of all, if we know that epsilon is the Gumbel distribution with the parameters of eta and mu, then the linear transformation v star plus alpha times epsilon, it's also a Gumbel distribution. And we know that with this transformation, eta will be v star plus alpha times eta, and for the second component, for the second parameter, that becomes mu divided by alpha. So that's one very important feature from the Gumbel distribution. And the second, the fifth one, if we have two Gumbel distributions, epsilon 1 and epsilon 2, with the parameters eta 1 mu and eta 2 mu, so they have the same value of mu but different values of eta, then the difference between these two, random variable, we say that epsilon 1 minus epsilon 2 is epsilon star. Then they will actually be logically distributed. We can find out the CDF. Sorry, this is a CDF. The CDF is 1 divided by 1 plus exponential mu times eta 1 minus eta 2 minus x. So this is the features between the two, about the distributions of the difference between two Gumbel distribution. This is quite useful for us to make a comparison between two utilities. And moreover, if we have j different Gumbel variables, Gumbel random variables, epsilon 1, epsilon 2 to epsilon j, they all follow the Gumbel distribution with the same value of mu, but they have different value of etas. So they have eta 1, eta 2, eta 3 until the eta j. Then for this j different random variables, the maximum value of this one also follows the Gumbel distribution, and you can find out the parameters for this maximum value. The eta will become 1 divided by mu times ln the summation of the exponential mu times eta, and for the second parameter it still be mu. So those would be the properties of the Gumbel distribution. And in the next, I'm going to show you how to use these properties to derive the probability for us to choose the mode I. So let's start with the property 4. First, let's verify whether the property 4 is correct or not. So we have mu epsilon is the Gumbel distribution, and this is the Gumbel distribution. And now we can try to define new variable t star as t prime as v star plus alpha t, and that give you the another derivation as t equal to t minus mu star plus alpha, and we know that t here follows the Gumbel distribution. Then you apply this equation, this component to the Gumbel distribution. To replace t, you can get the you can then get an updated expression for the revision. So to do a simplification, you can eventually gonna find that t prime gonna follow the Gumbel distribution, but the parameters modified a little bit. So eta becomes v star plus alpha times eta, and alpha becomes mu divided by alpha. So that's how we're gonna verify that the property 4 is correct. And now let's see how we're gonna derive the probability of choosing the mode I. We will need to recall here. We will need to recall the definitions of the utility. It has the deterministic component and random component. We know the distribution of epsilon j, and use the linear expression. We have u equal to theta times x plus epsilon j, And assume that epsilon j is in the Gumbel distribution with eta and with parameters eta and mu. And then we can do some apply the linear compositions to find out what's the expression of the probability. So for the uj, we can first add and minus one the same term eta. So this is still the same. Then we can go to check what happens about this term, epsilon minus eta. What's the distribution for that? So if we go to check the property of the property number 4, as we shown previously, so this one becomes the it just becomes eta minus epsilon minus eta. So it means that alpha is 1 here, and v star is minus eta. And if you put this assumption in the equation, you can get the quickly get the result as this term follows the Gumbel distribution with eta equal to 0, and we still keep the same mu value. And now we can conduct another conversion. So for this conversion, we can multiply mu on both sides. The equation will still be correct. And for this component, if you have mu times epsilon, then you can still recall the property 4 to see what the distribution looks like. So if we double check with this one, and you can find that this component actually follows an standard distribution, that is epsilon 0, 1. So this can be further simplified. For the utility, you get the result as you get the conversion as mu times uj equal to mu times vj plus eta plus and the standard Gumbel distribution. But you know that for the usually for the utility functions, we do not have any. We don't care about the absolute value. What we want is making a comparison among multiple utilities. So the absolute value of these two will be less important. So we can, in this case, we can just redefine the utility as mu times mu j, and with that, we will just assume that epsilon j is an IID Gumbel distribution, a standard IID Gumbel distribution with the parameters of 0 and 1. So this is what we will obtain based on the properties of the Gumbel distribution. And we will, from now on, we will just use the standard Gumbel distribution to represent the error term. Okay, well, with that, I would like to take a break, and after the break, we're gonna continue the introduction of the how to use the how to do some further derivation for the discrete choice theory we derived previously, to do the calibration and use that one to estimate the emission, or not to estimate the probability of choosing one mode. So before I set the break, is there any questions about the theory? It's a little bit complicated for you to understand all the details. but I still hope that you can check the procedure, the derivations in the slides. I showed the very detailed derivation. This will be very helpful for you to conduct your own research. Okay. Any questions? I cannot check the questions in the meeting chat, but if there's any, just let me know. Okay. Yeah. Yes. Go ahead.
So, for any techniques other than the MNL, like nested logic, cross-nested, or mixed MNL, will the error distribution will not be IID, right?
So for the nested distribution is a different story. We have some assumptions about some error terms to be IID, but for some error terms they are not, because they have some joint components about the different mode and different type of the mode, like the route and the transporting mode. Like you're taking a bus with the route 1, route 2, then we will have different random terms defined. In that case, the assumptions about the distribution will be different, but we will show you how we're going to set up the structure or set up different levels for you to conduct the nested logic model. That will be covered in the next in the lecture next week. For this week, we will just work on the simplest one, which we call the multinomial logic model for one single layer.
Okay. Okay. Thank you.
Okay. If does not have any questions, so we're gonna take a break and we're gonna resume the lecture at 4:23. Okay. In the meanwhile, I'm gonna turn off my camera and my voice. Okay, I guess let's resume the lecture today. So for the rest of this lecture, I'm gonna continue introducing the how the multinomial logic model is derived, and the method for us to do the calibration, and I'll possibly show you one example about how to calibrate it, how to use the calibration, the method for us to complete the calibration. There are a lot of derivations, there are mathematical derivations. I would like to show you the well, all the details has been shown in the slides, but probably I want to go through the details so that you won't be distracted or get bored about the hard part. Again, I probably need to exit the screen sharing one more time and then share it again. There's some issue there. Okay. For the multinomial logic model, this is the one that is commonly applied for the multi-choice in the transform planning. So this one totally relies on the discrete choice theory that we presented previously. So we have J different alternatives, and we define the utility for each one of them. And for the selections of the alternative, the utility should be the largest one. And we have the linear functions to show the relationship between the utility and the observed attributes. And in the utility, we have the random components and deterministic component. Regarding to the probability, based on the definition, we can find that the probability can be derived as the a function of the random term, and this equation applies to any distribution functions. But we usually assume a Gumbel distribution for the random term. And with that, we can then also we assume that this Gumbel distribution, based on the features of Gumbel distribution, they can be assumed as the standard Gumbel distribution with the parameters of 0, 1. And with that, we can then derive find out the closed expression about the probability, which will be something much simpler compared with the one that you see here. So with that, we know the standard Gumbel distribution, which can be written into these two expressions for the probability distribution function and the cumulative distribution function, with mu equal to 1 and eta equal to 0. And now let's see what happens. How we gonna find out, derive this expression to show the distributions, the probabilities for you to choose the mode or the alternative I. And to do this analysis, first we will do some transformation about the parameters. We assume that lambda equal to exponential of minus t, and with that, d lambda would be minus exponential minus t dt, which would be minus lambda times dt. This is a kind of quite useful transformation about the variables from t to lambda. And now we do some conversions, replace the t with lambda in this integration, and do some I'll skip the detailed derivation. But basically, if you do this kind of conversion, eventually you're gonna find out a very simple expression. So I'm gonna skip this one. So with this, for this whole integration, what you're gonna get is a very simple one. So this is the probability of the for the individual and choose the mode I, and you can see that this probability is only determined by the deterministic component from the utility. And also this is not the end. We can further simplify the expression by multiply exponential to vi on both up and bottom of this expression. With that, we get the multinomial logic model that the probability of the for the individual and choose I is the ratio of the exponential vi divided by the summation of the exponential vj for all the alternatives. So that's the simplified expression for the multinomial logic model. So it shows the probability for you to choose the alternative I. And now we're going to make a quick summary about that. So we assume that the random term follows in the uniform follows in the ID Gumbel distribution, standard ID Gumbel distribution, and we can find out the expression of the standard Gumbel distribution, and we will derive the probability of choosing mode I as the multinomial logic model. And also we know that for the constant term, for the deterministic term, not a constant, for the deterministic component of the utility is a linear function of the attributes. So we replace v with the function of theta and x. So with that, we have the probability of choosing I as exponential of theta times xi divided by the summation of the exponential theta times xj. So these two are defined as the multinomial logic model. So for all the derivations that we proposed previously, you don't need to remember them. What you need to know is about these two formulas. This would be the multinomial logic model that we derived from all the previous preparation, the properties of the Gumbel distribution, the conversions of the formulas, and so on. There are also another way for you to derive the multinomial logic model, which is actually based on the property 4 and property 6 of the Gumbel distribution. I will just give you a quick review about the process. So in the property 4, it shows the conversions about the a random variable. Say that we have epsilon follows Gumbel distribution, then v plus alpha epsilon is also the Gumbel distribution. And in the property 5, it shows that the distributions about the difference between two Gumbel distributions. We can find out the cumulative distribution function. Also from the property 6, it gives us the distribution of the maximum value for j different Gumbel variables, and it's also in the Gumbel distribution. So combine all these three properties together, we will be able to derive the multinomial logic model quickly. So this is what we get for the from the original definition. The utility of I should be higher than the utility of all the other alternatives, and which means that the utility of I should be higher than maximum value of all the rest j minus 1 alternatives. And apparently this one also follows in the Gumbel distribution. This is based on the property 6. It also follows in the Gumbel distribution. But what we do is that first we're going to check what's the distribution of Vj plus epsilon j. From the property property of 4, we can easily find out this distribution. But first of all, we assume that the Gumbel epsilon j is an ID Gumbel distribution with 0 and 1. And with that, from the property 4, we can easily find out that Vj plus epsilon j is the orthogonal Gumbel distribution with the parameter of Vj and 1. So that's the first part. And then we have this Gumbel distribution. We can then use the property 6 to find out what's the distribution for this maximum value. For the maximum value, if all this j random variable follows in the Gumbel distribution with the same value of mu, then the maximum of them is also the Gumbel distribution, and you can find out the value of eta, and also the mu value will be the same. In this case, we can easily find out that the for this what's the value of the eta for all these random variables. That would be the eta 1 would be v1, eta 2 is v2, and eta j is vj. So you put them together, you get the result of the maximum value as the Gumbel distribution with the eta equals to ln summation of the e exponential vj, and mu is still be 1. And then now you can apply the property 4 again to convert this distribution back to another one, back to the combination of two variables. One is the deterministic variable, the other one is the random variable, but it's the standard Gumbel distribution. So if we do this conversion, you can easily extract this component outside, and then it becomes the rest components in the standard Gumbel distribution. You can see if we want to know the details about the derivation, just try to check the slides after class. It will give you how these formulas are converted and transformed. And now we will apply this conversion. The maximization of the j-1 random variables back to this formula. And if we go to check this one, apply them back, you can see the for this equation on both sides, they have the standard Gumbel distribution, and they have two different deterministic components. And the probability actually ask us to find out what's the difference between two random variables. Then we can recall the property 5. If both of them follows the Gumbel distribution, then we can find out the CDF of the difference between these two random variables. And for this case, x will be this part. And we also know that eta 1 is 0, eta 2 is also 0, and the mu, both of them will be 1. Then in this case, you can quickly derive the formula for the probability of choosing the mode I. That one gives you the result as the probability is 1 divided by 1 plus exponential minus vi plus ln summation of the exponential vj, and you can do some further expansion about the components below. By time the exponential of vi on top and bottom, then you can expand it and simplify the whole equation, and eventually you get the same result, which is the same to what we derived previously. It's also called the it's the expression for the multinomial logic model, and we by introducing the linear format for the deterministic component, we get the another expression for the probability. So that's what we have to remember for the multinomial logic model. And now the tricky part is like how we gonna we know the expression, and we know if we are provided with the value of the theta, we are provided with the attributes of x, we will be able to calculate the probability of choosing each mode. But now the question is how we can use the observed data to calibrate this model to find out the right values of the theta. So the calibration is not that easy. In order to do calibration, let's sort out all the assumptions we made for the multinomial logic model and what's the potential issues we have to further discuss. So first, for the key assumptions, we assume that each individual in the model will try to choose the mode which can have the highest utility. So that's the first assumption, and also the utility is not a random variable. It has a deterministic component and also the random components. So uj is equals to vj, that's a deterministic component, plus epsilon j, that's a random component. Third, for the random component, the epsilon j, it always follows an independent identical Gumbel distribution, and is in a standard Gumbel distribution with the parameter of 0 and 1. And third and last, for the deterministic component, we assume that we can use the linear function to find out the relationship between the deterministic value and the attributes. So that is Vj equal to theta times xj. What we want to further investigate for this model is first, we need to calibrate the model, find out what's the values of the theta, how we're gonna use the observed attributes and decisions to do the calibration. The difficult part is like for the deterministic utility, we cannot observe it in reality. So we cannot apply the linear regression directly. And also for the decision, it's the probability. So what you can in reality you can see whether the individual take the mode or not, but you cannot identify what's the probability for this individual to take the mode. So that's another thing that is really hard for us to justify. What do we do? What we can observe is just the outcome, either 0 or 1 for the specific mode. And there are also some other issues we have to explore for this model. The first thing is about aggregation. We want to identify the potential elasticity of this model. Of course, it's very complicated, but it's necessary for us to verify whether the model is reliable and how elastic of the model to certain variables. And the other thing that we want to do is explore the IIA properties, the independence from the irrelevant alternatives properties. We want to check whether the independence assumptions is valid, and if it's not valid, how we're going to deal with that. And that goes to the last task, extend the model to different choice combinations, where we have to introduce the nested structures. For this one, I will just give you a very brief introduction about the nested structures to deal with like 2 or 3 layers. You don't need to really know all the details about the nested structure, which is quite complicated. Just to try to understand or have an ideas about how the model is used and how you're gonna if you are provided with calibrated model, how you're gonna calculate the probabilities. So let's first go to the first issue, the calibration of the model. So for the review issue, for the estimation problem, we have this in the prerequisite. We have reviewed some probability theory, and we also in the trip generation chapter we discussed the linear regression models, which will have some similarity here. For the estimation, we will first need to have the function, say that f. So the output y is the function of the input z and the parameter beta. Also, it has the random term. In this problem, we can further write this one to a simple format. In this problem, y is the dependent variable. It's the outcome that we can observe, and x is the independent variable that we can observe from the survey or from some data collection method. Theta is the parameter that we need to calibrate, and epsilon is the vector, is the distribution of the random term. And usually what do we know for this equation? It's like we know the functions. We know the functions of the f. Like if it's in a linear regression, we know this is a linear format, and we also know that this function has a random term inside. In addition, for the coefficient theta, those are totally unknown. Those would be the variables we have to estimate. And the distributions of the random term has been assumed, and in this case, it's assumed as the Gumbel distribution. And we can then use all the observed data, the dependent variable and independent variable, to conduct the estimation or the calibration of the parameters, the coefficients theta. And so in summary, y is the random variable and x is the vector of the known variable that can affect the distribution of y. So that's all the assumptions we make. And now let's go to see how we can conduct this kind of estimation or calibration. First of all, we assume that there's a population. That's the general start of all the regression issue. We have the population. This is where we want to calibrate the model. And the population has a lot of users, thousands, tens of thousands, or millions users. Apparently, we cannot know the information of all the users. What we do is like we're gonna try to pick up a small sample from the population, and that's doable. We will be able to select some individuals from the population to represent the general trend or the preferences of the whole city or the whole region. And in this sample, we will conduct a survey or try to apply some advanced data collection methods to get the dependent variable x and also know their decisions about the choice of the mode. So we have x and y from the for all the individuals in the sample. So this is only applied to the sample. And then we're gonna use the all the sample data, apply some statistical methods to find out the population parameters. what we do is like from the sample, we will have an equation, a method to calculate what's the value of theta. And we will then claim that theta is just an estimate of the true value. So here, theta tilde is the true value, but theta hat is just an estimate from the sample. It's not the true value, but it's close enough to the true values. For the linear regression, as we all know that in the if G is a linear regression, then that should be the least square operator. But for our problem, it's more complicated. Also, the realization of the theta hat is just the method, the calibration method. And we need to find out the most efficient method to do the calibration so that the theta hat is unbiased to the true value, which is deterministic. It's not a random variable. So so those would be the general background about the model estimation. Back to our specific problem, we have j different, assuming we have j different modes, and we have defined the functions for the utility. Utility is a linear function of the attributes. And also we have observed choices for each individual. For each individual we have something about their utility to each mode, and that will be something cannot be observed. But what we can observe is their final decision based on the utility. Say that if the individual n is choosing the mode I, which means that the utility of mode I is the maximum, is the highest one, and is always like the user individual is always choosing the one with the highest utility. And we were then able to find out the probability of the individual n to choose the mode I, which is the we can show in this equation. So the maximum of the utility, the maximum deterministic utility, and the random term should falls under the mode I. And so this is about the constant coefficient model. So the theta is it's a constant for all the individuals in the population. So that's the true value. But we need to do some estimation for the whole population. With that, we will recall the multinomial logic model we derived. So the probability of I is exponential vi divided by the summation of exponential vj. And we know that vj is the linear function of the constant coefficient and the observed attributes. And assuming that based on this linear assumption, we can further expand the formula for the probability. Where vj is the can read into the matrix format, and it can be further expanded as theta 0 plus theta 1 times x1 plus theta 2 times x2j plus theta k plus times xkj, and so on. So this is the linear expression we assumed for the deterministic utility. And now we have to apply the maximum likelihood estimator to find out the optimal values of the theta. This is a kind of the common method applied for the combination of the random variables and optimization issue. So what do we have is an observed data from the sample. We have x1, y1, x2, y2, and here get about xn, yn. So here n is the number of the observations. So n is the observations, a number of the observations, and for each individual, it has the decisions about the j different modes. So it could be the if the mode I or the alternative I is chosen, then yi is 1. For the other values, that will be 0. So that's the constraint for the multinomial logic model. So this is the we define this one as the chosen alternatives, and it could be written into the also written into the matrix format. And now, what we want to do for the optimization is like we will try to find out the joint probability of choosing of selecting y1, y2, y3 until get to yn. What's the joint probability of choosing this combination? And we want to maximize this probability given the observed attributes x1, x2, x3, and xn. So that's the key idea for the maximum likelihood probability. And also we have some assumptions about the observations. We assume that the observations are independent to each other. So the in that sense, the probability of y1, y2, y3, the joint probability will just be the products of the probability of each observation. So that is fy1 giving x1 and theta times fy2 giving x2 theta and so on. So that's the probability for all those n observations from the sample. And as we define this one as the likelihood function. What we want to do is find out the best values of theta. So we want to find out the theta hat to maximize the likelihood function. Now let's see how we're going to do that. First of all, we need to simplify this expression a little bit. So write them into with the product sign, and for the maximum likelihood of estimation, the value of the parameter theta should be selected to make sure that the observed n outcomes would be the most likely event in reality. So which is to maximize those probability. So now we can write down the maximization problem. In the maximization problem, we will just maximize the likelihood function, but you know that this kind of products is really hard for us to do the to complete. So what we do is like we're gonna apply the log transformation. This is some typical process to convert the likelihood function to the log likelihood function. That's what we're gonna write as the log likelihood function. With log likelihood function, we're gonna have the linear format. Then the calculation will be much easier. So now I'm gonna show you some details about how to use this log likelihood function to find out the best value of the theta. So with this log likelihood function, in order to find out the best value of theta, we're gonna try to find out the partial derivative of each theta. So we say that is from theta k. Theta k will varies from 0 to p. So we have p plus 1 equations, and we have p plus 1 unknown variables for theta. With that, by solving this those equations will be able to find out what's the optimal value of theta. And also in this, to solve this problem, we have to make sure that the second order derivative, which will be the Hessian matrix, should be negative semi-definite. In that sense, we can then make sure that the solution exists. Otherwise, we cannot get the right answer. So we have to first make sure that this one is a negative and semi-definite. Now, for the rest of the several slides, I'm going to show you some. Well, I'm going to show you some details about how to do this derivation and how to find out the best how to find out the value of theta k. It's very complicated, so I will not go through the details about derivation. Well, if you are interested, you can go back to check the details by yourself after class. So I will go through them quickly. So for the multinomial logic model, basically we will just try to replace the probability with the one that we derived previously, and then you can replace the Fyn given xn and theta from the likelihood function, and usually, even though you see it's very complicated, but what you're gonna see for this case, for each observer there's only for each individual there's only one mode is selected, so most of the other for the other mode that is not selected is not chosen, so you only choose the one that will have the value of the outcome of 1 instead of the others will just be excluded from the expression. And with that you can continue the derivation. I say that I'm gonna skip those detailed process, do the log transformation, and try to expand the expressions and try to simplify, cancel some common terms, and further reduce the complexity of the system. And especially here we have the linear assumptions about the model. So replace the deterministic component with theta 0 plus theta 1 x1 plus theta 2 x2 and so on, and do the derivation, the partial derivative for all the thetas. So as I say, that is very complicated, so I will skip those derived detail. Eventually you can actually find out some very simple expression for the result. Let me just skip those steps, the detailed derivation steps. So you will, okay. So here's the part for us to make a summary about the derivation. So first of all, we have all these assumptions. We have the multinomial logic model. We have the linear format about the deterministic component. We have the definitions about the attributes, the unknown variables, and also some constant coefficients. Here I will give you a reminder about the definition of one component. So in the linear regression, we have to set a constant coefficient. But for the multinomial logic model, as is only applied for us to estimate the utility, so the ideally it's not necessary for us to set the constant component, because it will be the same to all the utilities, which means that it will be meaningless for the comparison to to check which one is higher or which one is smaller. So what we do is like we will skip that component, but we will introduce another constant, which would be x0i, and this one applies to some of the mode. Say that you have let me just consider the example about CN with three different modes. The bus, train. What happens? Train and car. So ideally, you will have the VI equal to theta theta 1 x1 plus theta 2 x2 theta p xp. But that's for the that's just for the mode I. For the mode I, so xi. For the mode I, for the linear regression, usually we will have the constant term. But as you're gonna see that for the v1, v2, v3, if they all have the constant term, say that sorry, just write it. So they all have the constant term plus something. Then it's meaningless because we just need to check whether v1 is higher than v2 or not. If they both have the constant term, then it's not really not necessary because it does not play any meaningful comparison. So what we do for this constant term is like we can assume that there's another dummy variable, which is x0i, with respect to the constant coefficient, and x0i will be zero for some alternatives. Say that if it's a car, then it's 0, but if it's a bus or train, then it's 1. So with that, you will have some meaningful result, which means that if it's say that the bus is 1, mode 1, train is mode 2, train is mode 2, and the car is mode 3. In that case, we will have theta 0 plus something. For the mode 1, we have theta 0 plus something. Mode 2, we have theta 0 plus something. But for mode 3, we will not have the theta 0. Instead, we start with theta 1 x1 3 plus something. So with that, you will have the meaningful comparison between mode 1, between the mode 1, the bus and the car, and the train and the car. So that's the reason for us to set an dummy variable, and this is also very important for you to conduct the multinomial logic model. We call this one as the alternative specific constant. So you can select this definition based on your own needs in the for the specific problem you are trying to work with. There's no standard about which mode should be set as 0, which mode should be set as 1. Just select some of them as the comparison. And now let's recall the maximum likelihood estimator as what we derived previously. So we will for all those k plus 1 equations, what we derived is this equation. It's still complicated, but it's better than what we showed previously from the likelihood function. And we know the yi is the potential outcome for the individual n. And once you solve this equation, you will have a set of the parameters p plus 1 coefficients estimated. But now the issue is like even for this one, it still be very complicated. We need to find out a way to a simple way that or a way that we can complete the computation. Say maybe not by hand, but you need to find out the logic that you can do the iteration and complete computation through with some computing programs or some computing tools. So what do we do? It's like we're gonna try to rely on some Taylor expansion and try to apply some this kind of Taylor expansion to do the iteration. So for this complicated p+1 equations, it can be written into the matrix format. It's f theta equal to 0. So we have p f theta. It's in the p+1 matrix. It's p+1 vector, and we know the expression of each cell in this vector. And now we're gonna apply the Taylor expansion. This is apply Taylor expansion to expand this p+1 equations, and then deploy the Newton-Raphson algorithms to conduct the iterations. Well, it can help you to quickly find out the solution, the optimal solution of the complicated, a very complicated formula. So for the Taylor series expansion, for the general function, fx equal to fx0 plus x minus 1 times df divided by dx at x equal to x0 plus half of x minus x0 square times d square fx to dx square at x equal to x0, and so we can get a lot of higher orders. With more higher orders, your estimation will be more accurate. And for this case, for this specific case, as f is in the matrix, then you need to find out the derivations, the partial derivations for the matrix, for the vector, and this is just the Hessian matrix for the for those vector, and here you're gonna see the details about how the what's the matrix of the partial f theta looks like at some specific value of theta m. And now you can then go to see what happens if the f theta equal to 0. That is the optimal solution, where the optimal solution stays. Usually what we do is like for this calibration, we will not consider some the components with the higher orders. We will only consider the first order derivation, that is delta inverse delta f theta, and with these derivations, we can find out the formulas for the iteration, which is from the Newton-Raphson algorithm. With that, we have theta equal to almost theta m equal to theta m minus the first order derivative of f theta at theta equal to theta m inverse times f theta at theta equal to theta m. So this is the equation that we're going to use to do the iteration, and we need to find out the value of f theta given theta equal to theta m, and the first order derivative of f theta at theta equal to theta m. Once you have these two values, you will be able to apply this equation to find out the value, to do the iteration, and eventually find out the optimal value of theta. So here, let me give you a summary about the steps to do the calibration. First of all, we need to have some initial guess about all the values of the theta. The most common initial guess is to set all the values as 0. So initially set all of them as 0. And in this case, if all of them are set as 0, which means that the probability of one individual to choose any mode will be the same. If there are three modes, then the probability of choosing each one of them is just 1/3. So that's the that means that we don't have any information about the preferences of the individuals. And then in the next step, we're gonna apply these iteration equations to keep on updating the value of theta. So we have to find out the value, the expressions of f theta. We have to find out the expressions of the pressure f theta, and find out this matrix at the based on the initial guess of the theta. So that is 0, 0, 0. And once you have the value of pressure first order derivative of f and the value of f theta m, you can then give us an update of the theta m plus 1. That will be the value of the theta in the next iteration. And then just go to the continue the step 2 for multiple times until you find out the difference between the thetas at the 2 iterations will be small enough, then you can stop the iteration, and that one will be the estimated or the calibrated value of the theta. It's the whole process is simple. The only difficult part here is the calculation of this matrix to show the first order derivative of the f vector. Of course, if you have, say that if you have the value of p is large, then it will be very difficult for you to conduct the calculation. But if you have less number of the attributes, like a p equal to 1, 2, or 3, then it's still able for you to do it manually or write your own code to conduct the estimation. So that's the so as I say that for the in this calibration, the most difficult part is finding out the expression of this matrix. And now let me give you some information about how the matrix is derived. Assuming that we have we consider the one cell of the f functions in the for the individual n, and that's what the expression looks like. And now we want to find out the component of partial FL divided by partial theta k, which would be any random cell in this matrix. And now we can do the derivation. Again, I'm not going through the details about the derivation. It's very complicated. You can go back to check the details by yourself after class. By using the multinomial linear regression model, the expression for the probabilities, we can then get some derivation to try to simplify the formula. Let me just quickly go through jump to the conclusion of this derivation. So this is the one about the derivation of all the expressions of the component for the cell at the row L and column K, and you can also find out some further simplification about this formula as the based on the assumption that the summation of yi equal to 1, and eventually you will get the you're gonna get this one. You will get this expression to show the calculation of that component, which is the function of the probability to choosing the mode J, and also the attributes, some observed attributes at the specific mode and the specific attributes. It's very complicated. So what I want to do is like give you an example about how we can apply this calibration process to a simple problem. So what do we do? In this example, we will consider a simple example with only 21 observations. And for each individual, each observation, they have two different modes to take, either car or bus. So that will simplify the estimation a lot. And in the data, you will also be provided with the information about whether the individual is taking the bus or taking the car. So with that, we have to summarize all the information that we can extract from the table. First of all, we have 21 observations or 21 individuals. And second, we have two different modes, car and bus, assuming that the mode 1 is car and mode 2 is bus. So that's our assumption. And then for both of them, we have the information of the travel time. So we will be provided with the travel time of the car and the travel time of the bus. And this means that we will only, the first variable we're going to use for the model is travel time, regardless of the mode. So that's the one parameter we're going to use, one attribute we're going to use, travel time. And also, you know that we have to set another constant or the dummy variable, which is the x0. For this case, in from definition, the dummy variable should be applied to some mode, but for the other mode, it will be set as 0. So in this case, we can assume that for this dummy variable, if it's a car, then the value is 0, and if it's a bus, then the value is set as 1. So this is a very important step. If you don't have this step, it will not be easy for you to differentiate the selection, the decisions between the car and the bus. So we have this dummy variable x0i as for the bus and the car. And now we will have the two formulas. For the utility of the car, that is V1 equal to the deterministic utility. That is V1 equal to theta 0 times x0. For the car is 0, so we can remove this component. So V1n is just the theta 1 times t car. And for the bus, that is V2n equal to theta 0 times x02. In this case, x02 is 1, so we have theta 0 plus theta 1 times the travel time of the bus. So that's the definition of the deterministic utility for car and bus. And now we can find out the probability. We can find out the probability of choosing the car and the probability of choosing the bus from the multinomial logic model. So that is for the car is the exponential of the v car divided by exponential v car plus the exponential v bus. And you can also find out probability of the choosing bus. So we can then write them based on the definition of the deterministic utility for the car and bus. replace car with this equation, replace bus with the second equation, and now that's the two utilities, two probabilities we assigned for the bus and the car. And then the next thing is like we have to conduct the calibration process. In the previous slides, we have derived the formula of FL, and that equals to the summation of n from 1 to n. That's the observation. The summation of I equal to Cn, that will be all different modes. And then that will be yin times xli minus summation of xlj times the probability of choosing j. So that's the expression for the FL theta. And in our case, we only have two modes, so we only have F0 and F1. You can then get the full expression for this problem. What we do, like for the observation, we have n equal to 21, and for the Cn is just 1 and 2, so there are only two different modes. So we can apply this one to our specific problem with n equal to 21 and Cn equal to 1 to 2 to do the and also for this one to expand this formula. Also, we have the as we only have two modes, so this one can be simply expanded. So that is x01 times the probability of 1 minus x02 times the probability of x2. Similarly, can get the information for the second equation. So that's for the f theta. And we will then load the information of the multinomial logic model in this equation for the f theta. So we have the exponential of the probability for the car and the probability of the bus. And it will get very complicated for this, definitely for this case. And also you can try to check what's the value of the 0 and 1 for the car and bus to simplify your derivation. And again, this is become complicated, but we can try to simplify some components. So I will skip this simplification process. Once you do this kind of simplification, you will find out the simplified expression for the two elements of the vector, but those are all related to the n21 observations. So that's the first step. Find out the expression of the f theta, and then we need to find out the first order partial derivative for the f theta. Luckily for this case, we only have two different attributes, and two coefficients we have to estimate. So the size of the this matrix would be just 2 by 2. So which means that we only need to find out the expressions of these four components: partial f0 over partial theta 0, partial f0 over partial theta 1, and so on. So the well, again, we can just cite the expression that we the conclusion we get from the previous analysis, and with that we get the I'm gonna skip those processes. It still comes from the previous derivation. So what you can get is about the all the four components. So you get all the four components for the pressure f theta, and also the f theta, the function of the f theta. In those equations, in those two equations, is related to the observations. And you can then recall the iteration process to find out what's the value of the theta. In the first iteration, theta will be 0, 0. And if you apply theta as 0, 0 to these two equations, you can calculate the probability. You can calculate probability of choosing mode 1 and choosing car and choosing bus based on the travel time and the dummy variable, which means that you can find out the delta f theta and f theta. So these two are vectors matrix, and then we can get the say this is a theta 1. Then in the iteration 2, well, of course, here need to get an update and get a theta 2 equal to theta 1 minus f theta and then you have this new theta value, theta 2 values, find out the value of f theta 2 and do the iteration, get a theta 3 as something related to theta 2 and iteration 3, do the similar process, get a theta 4. At every step, you need to check the difference. Check the difference to see whether it's smaller than certain value. If it's smaller than certain value, you're gonna stop, and then you can get the calibrated value for theta. So that's the whole process for you to conduct the experiment, and I hope you can. I'll just stop it at this step. I hope we can come back to go through the whole process by yourself. Actually, for the last homework, there's one problem similar to this one, similar to the there's one problem similar to this example. So what you need to do is trying to complete all the process and get the result of the theta, how the parameters are calibrated, and then you will have a better understanding about the whole calibration process and the implementation of the multinomial logic model. Okay, so with that, I will stop here, and I would like to see whether there's any questions or comments about this. Okay, if there's no question, then I will just stop here for the lectures. And regarding to the let me try to get the. Regarding to the I would like to take you like probably 10 minutes to give you some explanation about the solution of the homework. Okay, so for the homework, not homework, sorry, for the midterm. So for the midterm, for the first problem, this is the I guess it's the a little bit tricky for you to work on. So for the problem 1, we will consider the conditional probability and joint probability and how to find out the full probability. So in the problem, you are provided with the conditional probability of x given r. So it's the probability of x given r is actually follows in the Poisson distribution. This is the one typical Poisson distribution. For the Poisson distribution, the mean value is lambda and sigma. I guess the variance is also lambda. If I remember correctly, yeah. Yeah, that's what I remember. Yes. So now you need to write down the probability distribution of the trip. So it's like you want to find out what's the probability of x. So in this case, you need to recall the definition of the joint probability. So for this one, that should equals to r equal to 0 to 4 for the joint probability x and r. And for the joint probability, there actually has a relationship between the conditional probability and joint probability. So for the joint probability, we have x given r times the probability of r. So we have the expression of the x given r. We have the expression of the r is in the discrete random variable. So if we just write them together, you can get this expression about the probability of x. A lot of you just write down what's the expression under one specific value of r. It's still be the conditional probability. So that's not the right answer. But I'll value effort to try to find out the probability. Basically, for this problem, just try to understand how you're gonna remember about the relationship between the joint probability and the conditional probability. So that's the first question. It's quite simple. And for the second one about the mean value of the distribution, so we're gonna try to check. Start with the definition of the mean. So this is the definition of the mean. The expected value of x is the summation of x from 0 to infinite. For Poisson's distribution, x should be higher than 0. Then we will have the full expression for the from the first problem, and as you can see that you can actually put them into a separate component. So for the first one, you have for this expression, you have first component as the summation of x from 0 to infinite times x, not time, x times the 2x exponential minus 2 divided by x factorial times 0.3 plus summation of x equal to 0 to infinite x times 3x exponential minus 3 divided by x prime, and so on. So you can see that this part, it's just the expected value for the Poisson distribution with lambda equal to 2. So what you will get is for this one, it's a point for the Poisson distribution. The mean value is as I say, mean value is lambda. Variance is also lambda. So we get a 2 times 0.3 plus 3 times I forgot. This is a 0.5. 3 times 0.5 plus 5 times 0.1 plus 8 times 0.1, which will give you the result as 3.4. So that's how you get the variance, the expected value of the proposed distribution. And similarly, you can apply the process for the variance. It's a little bit tricky. What we can do is we're gonna work on the variance for each component. Let me just take the first component out so you can see how you're gonna work with the rest one. So for the first component, you get x from 0 to infinite, x minus 3.4 square times 2x exponent minus 2 x factorial times 0.3. But what are you gonna do? Let's do some expansion. Say that for x minus 3.4, it can be written as x minus 2 minus 1.4 square. That is x minus 2 square plus minus 2.8 x minus 2 plus 1.96. And for the first component, here, if we put this one with this part, it's just the variance. A variance of the Poisson distribution with lambda equal to 2. And for this one, you can actually get this one as 2.8 x times that one, so which will give you so what I can get is the first component minus 2.8, the summation of 2.8 x times 2x exponential minus 2x factorial plus this part, this 2 will be 5.6 plus 1.96, 5.6 plus 1.96 times the summation of 2x minus 2 x factorial. So this part is just 1. This part is just 1, and this part is still be lambda, that will be 2, and this component is also be lambda, that will be 2. So with that, you can calculate what's the value for the first component, and similarly going to apply for the rest component. Once you complete all the calculation, you get the value as 7.232. So that's the solution for the first problem. And the for the second problem, I know a lot of you are working on the finding out the ratios directly, but you can get some similar result. The result will be close to the one that I get here. But there are some simpler method for you to get the solution. So in this problem is actually designed for you to understand what's the definition of elasticity. In this problem, we assume that there's a function between the number of trips and the properties of the features of the trips, like the travel time of the auto and the bus, the cost of the trips, cost of auto and transit, and the first problem wants us to find out what's the what happens if the auto cost is changed from $5 to $6, And this one, if you recall the definition of the cross elasticity, it will shows that what's the percentage of the volume changes with respect to the percentage changes of the price or the cost of any variables. For this case, we will try to find out the cross elasticity of the volume with respect to the cost of the auto. So that is a partial V over V divided partial CA over CA. And in this case, you get the result as minus 0.5, which means that if we increase the price for $1, it will actually decrease the or not for decrease. If we increase the price from 5 to 6, means that you will increase about 20% of the price. It indicates that the demand will decrease, or the volume will decrease about 25 or 20 times 0.5%. That is 10%. So in this case, what we get is the reductions of the trip is of 10% of the total trip, that is 5,000. And similarly for the transit, they say that the transit time increase reduced from let me see, the reduce the transit time from 1 hour, which will be 60 minutes, to 45 minutes. That is about 25% reduction. You can then go to check what's the cross elasticity of the volume with respect to the transit time. That is minus 0.15. In that sense, the volume increase will be 25 times 0.15, and it can be shown in this equation. So it shows that the volume increase from the transit time reduction is around 1687, and you can find out the combined reductions about the updated volume of the trips with respect to the changes of the cost for the auto and the reductions of the transit time. So that's the first two problem, and for the rest of the questions, all the class are doing very well. So I don't think it's it's not necessary for me to go through them. If you have any questions about it, just let me know. I can explain the details about it. Okay. Any questions? Any specific questions about the lectures and also the midterm exam? Okay. If there's no additional questions, I guess that will be all today. And just feel free to let me know if you have any concerns. You can also drop in the office hour or send me email at any time. Okay. Well, I think that will be all today, and I really appreciate the time in the class. Well, I'll upload